kind of more obvious that this is really a process that's going on because something is changing. But yeah, this is an oscillatory behavior between two values. So this is kind of interesting. At least I think it's interesting because I did not change the model, right? It's the same model. The only thing I changed was what the parameter is doing, A. And this already gives us like 6 qualitatively different behaviors, right? Because you can describe them as exponential growth, exponential decay, steady state, oscillation between 2 points. What did we have? Exponential increasing oscillation and exponential decreasing decay. So really qualitatively different behaviors. So if you would sort of consider this like the output of really a system that you're interested in, and this is what you find by doing experiments. You figure out that this parameter means something. Yeah, by describing the patterns that you see for these different values, you would have created an order parameter for the system. And you could actually create something that's similar to this phase diagram. So you can sort of figure out, okay, for these parameter values, I see this behavior, you can make a nice picture. That's actually what we're going to do next. But you can apply these concepts that I talked about to the amoeba and for the flock to these models. So the control parameter would be, of course, A. Right? So A decides what the behavior is that you're going to get. So that would be then the control parameter. And especially if you compare it maybe to the linear models that you're used to, like maybe a regression model, yeah, they only produce lines, right? Maybe if you put in polynomial stuff, but then you're actually putting in nonlinear stuff. Yeah, a linear growth model is really something that is in completely different in that sense. Yeah, and the role of time is part of the model because we are iterating it, right? So that's really where time is. So we already assume that time is there, and it's a crucial part of what this model is doing. We assume it is flowing, and we don't have to think about whether that's true or not. That's just the case. We are describing an evolutionary process. We are describing a change rule. Right? So what happens to this value over time? Yeah, at least 4 different types of behavior. And so we don't have to add any predictors to get this. It's just changing the control parameter that will give us this different behavior. So that was kind of, yeah, already kind of interesting, but of course it's one of the simplest models. The next model is the Logistic Map. It has also many different other names, and it's used very often. So the model that I'm showing you is kind of a toy model, but it has really actual applications in ecology. There are population growth models, and this is kind of the simplest version of it. It's also sometimes called a restricted growth model. And I'm going to talk about the Logistic Map, so the discrete version of it. Here I exchanged y for L, doesn't really matter. It's mathematics, so you can use anything, and I exchanged A for R. So if you look at it here, it's a little bit different, but we still have, this thing is just actually the linear model, right? So we had A times Y, but now we have R times L. That's really the linear part, but then we are adding something here. So it's not just that we have to multiply the current value with R, but we also have to, well, multiply it with 1 minus what we already have. And so we'll talk about what the function of this thing actually is, but it's not overly complicated, so we just add this part actually. Right? So this part is just added, and the rest is what we already saw. So it's the simplest, non-trivial model used as a as an introduction to dynamical systems theory, but especially the second part to chaos theory. Because this model can produce something called deterministic chaos, and we'll talk about what that is. So well known in ecology, social sciences, well, if you're at our department, it's fine. But actually, I think that one of the earliest entries into the record of psychological science was by Paul van Geert from Groningen, which was already in 1991, I think, for language growth. Oh, yeah, next meeting that should be also be taken out because we're doing the short version of the course. But I will put up the link to his paper, and he's using this model to model vocabulary growth in young children. And it's really this version of this model. And I think it's 1991 or something like that. Okay, so let's do. Oh yeah, so I told you the linear map has a solution. Well, here already for the logistic map, that's not possible. So I'll show you what happens. So if you try to do the same kind of game and fill in everything, you get this really messy thing with lots of. It's really not possible to find one compressed rule that will give you, any the value of what's going on at any time point. So this already does not have this equation does not have a solution, and not have an analytical solution. So if you want to know what's going on, you really need to do the iterations. You really need to do the work. Okay, so let's do this, and let's take some values for R. So they're now maybe a little bit less intuitive than in the linear model. But these are the values we'll use. And so because of the way this is set up, this model, R can be between 0 and 4. We can talk about it later why that is, but that's sort of the range for R you can have. And we'll take the initial value as just a small value and see what happens. Okay. So this shows you why it's called the logistic map, because you might know that these kinds of shapes here are the logistic function, and the reason, so the logistic, you might have done logistic regression, those kinds of things in statistics. But those are based on the continuous version of this model. And the continuous version of this model does have an analytic solution, which is why you can use it in statistics. So, yeah, this is one of the reasons why it's called logistic, this S-shape. But what it means is that you start at a value, and this initially starts to grow, then it attains some maximum growth, and then it levels off, and it doesn't grow anymore. Right? That's usually what logistic functions are used for, or to model systems of variables that can have only two values. So that's maybe not very impressive. Let's go to the next value, 2.9. We see something like this. This little part here, we already saw in the linear map, right, for one of those negative values. And now it turns up here. So first we have some growth, it goes to some level, then it oscillates, and it ends up in this at this value. So this type of behavior, I'll say that again next in one of the next slides. But what we call this type of behavior is transient behavior. So first, before the system can settle into a kind of stable state, we have this period where it's sort of doing a lot of things, and then it dies down and stays at one value. At least for this parameter setting, it stays at one value. Because if we go to the next slide, this we already also saw, right? So for -1 in the linear growth model, But now it settles in a state, we would say, in an, actually we would say an attractor state, that is oscillating between two values. Right? So first we have some transient behavior, and then it settles in an attractor state that switches between two values. 3.3. Let's take another one. 3.52. What happens now? Well, we have again some transient behavior, and now it's oscillating between 4. 1, 2, 3, 4. Between 4 values. So we started out at 1 value, then it ended up in 2 when we increased this. Now we're at 4. Well, let's see what happens. Next. At 3.9, we see something like this. And this is actually a very special behavior, because this is what is called deterministic chaos. What is happening? At some value of 4r, the system will not end up in a neat oscillating attractor that has very discrete values. But actually, in fact, we know that none of the values that are in this sequence will be repeated. So they are all unique values. What you can see, however, is that there are some patterns that are sort of repeated, but not exactly. So you will see that there is some structure in here, or apparent structure, but none of the values are ever repeated. And that's very odd, right? So what is going on here? I'll tell you before I tell you this. So again, we have this kind of simple model. It has shown us, well, qualitatively different behaviors, and even something that well, is kind of very weird and interesting, but it's the same model. Again, the only thing that we're doing is changing R here. This is of course very powerful for modeling all kinds of complex phenomena, and it has been used for very different. So what I'm talking about here is actually called stylized logistic, and it has this 1 here, but in more realistic models, this 1 actually also becomes a parameter of the model. So you can change 1, and it usually is K or C or something like that, and it is reflecting something called the carrying capacity, especially if you're talking about population dynamics. This actually decides how far the system can grow. So it's the carrying capacity of the environment very often that is indicating how much of a population can be sustained by the environment. Okay, so again we have not really complex model. And we have a control parameter that is deciding what kind of qualitatively different behaviors we will get. So the question now is, what can we do to study the system? How can we in some ways summarize, or can we know something about the different behaviors of this system? I already told you about the phase diagram, and for this particular case, this is called the bifurcation diagram. But it is actually a description of what happens for different parameter settings, what kind of behavior do we expect. And then the type of behavior would not be the transient stuff, but where does the system end up in, basically. Yeah? And it's you can think about this as a phase diagram. So what is the system doing for different values of the control parameter? So this is just to remind you that the parameter is called control parameter. So the end states we would call attractor states. Right? This is where the system is attracted to. And it means that if you have a specific parameter setting, it doesn't really matter what initial value you have. You will always end up in this attractor state that is given by the control parameter. So if you change from one attractor or set of attractors to another one, this is called a bifurcation in terms of the mathematics. But of course, we could also call this a transition, a phase transition, or an order transition, because we're going into a different type of dynamics. If you want to model water going to ice, you could think about it like that. It's really a transition that is giving you a qualitatively different behavioral state. Okay, and there are different types of attractors. So we've seen if it goes into one steady state, we would call this a fixed point. And the way to actually write this down graphically for one-dimensional systems is like this. So in this case, it's a stylized logistic function. Let's say it can vary between 0 and 1. This means that this is the value of the values the system basically can take. But this means that it doesn't matter where you start out with for your initial value, you will always end up at this fixed point. And in this case, for 2.9, it's something like 0.6 or something like that. So if you have this type of attractor, this would be called a limit cycle. What does it mean? You can start somewhere, you have some transient behavior, but once you get to one of these points, you will just be going round and round. So it will just flip between the 2 points. Or you can also start here, but you will very soon be directed to one of them, and you will end up in this cycle of points. And this would be a limit cycle period 2, but we've also seen you can have limit cycles of period 3, 4, and then you would get these nice jumps on this line. Now, we've also seen this behavior, which I called deterministic chaos, which actually, was difficult to describe in terms of periodicity or in terms of going to one value. So those types of attractors we would call strange attractors. This is from a much more complex system, but this represents the different types of values that this system can have when it is in this kind of chaotic state. And there are some characteristics of this behavior that we can say something about. And one of the things is, so suppose this black square here represents all the values that this system can potentially occupy. We can say, and that's why we still call it an attractor, it is bounded. So it's not the case that it is everywhere. If you would have a random system, it would end up filling up the entire space. So, but that's not what's happening with these strange attractors. They are still bounded to regions of this state space. It's quasi-periodic, which means you probably have, some trajectories going on here, and it will probably follow a very strange trajectory through the space. And it's not exactly periodic, but it's quasi-periodic. It is following something. It's just not the same every time. So quasi-periodic and bounded are two of the characteristic features. But in general, it just means that what is an attractor for a dynamical system? If you think about all the potential states the system can be in, an attractor just means it does not occupy all those states, and it's not expected to occupy them in the future. No, it is just attracted to a specific limited region of this space of potential states. If you want to talk about this in terms of degrees of freedom, right? So all the states that are available to the system are its degrees of freedom. And what does it mean for a system to be in a specific attractor? It means not all the degrees of freedom are available to the system. So the system is constrained in its behavior. The degrees of freedom are constrained, and very often this gives you these interesting patterns. So if we go back to the logistic map and the bifurcation diagram, we can draw something like this. Okay? So this would be what y can become, or L, I use L, right? And here we have what R is, what the control parameter is. So I said it can be somewhere between 0 and 4. And the only thing we do is, so what happens if we make R1 or 0.5? So they end up at 0, I guess. So at 1 things start to happen. And we just plot in the values we get from the attractor, right? So in the beginning, this is just one value because it ends up at this fixed attractor, right? So if you increase it, the fixed point you end up in will increase. So the parameter, the end states, and yeah, at some point, at 2.9, right, and that's somewhere here, we ended up in, I said something like 0.06, or 0.6 is here, so it's just a little bit above 0.6, right? So that's that point, right? So that's for parameter value 2.9, that's this point. It ends up here, okay?
So we ignore the transients.
We ignore the transients, yeah. Yeah, we just take the end state. And then at 3.3 we had this, right, so here somewhere we get this limit cycle of period 2, and that's represented here, so 3.3, somewhere here, I don't know, it's those two values around, what is it, 0.5, or actually a little bit more here. But it's those two values that it's oscillating between, and this continues, so it does this band of oscillation becomes larger and larger until there is a point over there, right? Where it turns into 4 points. So that's why it's called the bifurcation diagram. So far at each point it's just splitting into more limit cycle behavior of a higher period, from 1 to 2 to 4. And then you can see here you get 8. Yeah, 8, and then here something is happening, right? So yeah, here we have the 4 or 8 point, and this is called the chaotic regime. Actually, it's not the entire thing is the chaotic regime, because you can see here at some point it pops out again. But it does have all the characteristics of the definition of the attractor, because it's bounded, right? It's not, if this line here is the state space of the system, so these are all the values it can be in, this is the degrees of freedom of the system, it's still not occupying everything, right? So it's bounded, and it's quasi-periodic. Which you cannot see from this diagram, but 3.9 is somewhere there. And if you wait long enough, then this bounded region will eventually become darker and darker and darker, because each time a new point is added. So the outcomes here are, of course, numbers with many decimal points, right? So they're not rounded in any way. Yeah, so in the chaotic regime, the system will never return to exactly the same value, and these bands will become almost black. It will not fill the y-axis completely, so it's bounded, right? It does not occupy all the available degrees of freedom. So it's an attractor, but it's a strange attractor. And this is from a different system. But you can see there are, this is I think the Hasselman map, yeah, you can look it up on Wikipedia. And you can see that, and this also happens in the Logistic Map, but you can have regions in which it is displaying this chaotic behavior, and it pops out again, and then it goes into, and then out, and in. And these lines you see here, I actually don't know what they are, but mathematicians study them and why they appear and if they can formalize what's going on there and it's I mean that's still also the logistic map is still being studied by mathematicians. So it's very interesting, and it's if you think about it, it's really not a very complex model, right? It's just one parameter. And we have only the rule that time is flowing, and you get this very interesting behavior. So just to finish this part, let's talk about what we can say about deterministic chaos, and also maybe demystify it, not in the sense that it's not amazing, but it is just something that pops out of these very simple models, and we can observe phenomena like chaos in nature. For instance, if you see, so turbulence is actually chaos, but in 2 dimensions or more dimensions. So. And if you're on an airplane and you experience turbulence, then that's actually the state of the atmosphere, which is best described as chaotic, but it's like chaotic movement of molecules in a volume, so in 3 dimensions, or you could say in space and time. So here are some nice quotes. Richard Feynman, Horace Lamb said, when I die and go to heaven, there are 2 matters in which I hope for enlightenment. One is quantum electrodynamics. Well, Richard Feynman gave enlightenment on quantum electrodynamics, by the way, but this was after his death. But the other one is the turbulent motion of fluids. And about the former, I'm rather optimistic, which was correct, because Richard Feynman gave us the theory for quantum electrodynamics. But then, of course, Richard Feynman is also still puzzled about turbulence. And so, here you can see what turbulence is, and it's very common. So this phase here, where the smoke is neatly going up, the smoke particles are all doing the same thing. That's kind of a ordered or a laminar phase. And then this quickly breaks up and becomes this puff of smoke. And what you see going on in smoke is really turbulence. It's turbulent motion of the air, and it is really chaos in time and space. So in terms of modeling, this is from a book called The Art of Modeling Dynamical Systems, and so this author makes a kind of distinction in types of phenomena and types of models. If you can read it, I don't know if you can, but the type of model that we are talking about now is called type 3 model. So it's a quasi-deterministic model, chaotic dynamics, and it is characterized by, well, if you would only look at the phenomenon, right, you would see something that looks random, but it probably is not. That's actually the definition that Lorentz gave us of deterministic chaos. It's stuff that looks random but is not, because it's actually described by deterministic process. But the thing is, if you think about what we are actually usually doing, you have solvable dynamical systems. I showed you that this very simple model, this linear growth model, is solvable. In continuous time, you have some more complex models that are solvable. The linear models, they are actually not really in this. The linear models that we use are not really in this, or maybe they are somewhere purely stochastic models, maybe. The discrete logistic equation. Yeah. So the discrete logistic equation is what we just covered. And you can see that we are, in terms of complexity of models, we are already pretty far into the hierarchy of models that are possible. But in terms of complexity of the mathematics, I think you would agree it's not really very difficult to master those mathematics, or to understand at least what is going on. So there's no real definition of chaos, but it has at least 4 ingredients. Okay, so the dynamics is aperiodic or quasi-periodic. It's bounded, so it's not random, because it does not, also not with infinite time, visit all the possible degrees of freedom. But it is deterministic, and the second one is probably the most interesting one for behavioral science. These things are sensitively dependent on initial conditions. So this means that, so if you take this parameter setting of 3.9, right, and I ran it with a very specific value of y0, so I started somewhere at some value. But if you make a very small change to this initial value, you will end up with a completely different pattern. It will be also very much deterministic chaos, but it will be nothing like the pattern that you got with the other value. And actually what you can study, and you are going to do this in a spreadsheet, you can study how long it takes before the two values are going to diverge. So this is actually a measure that is used in studying these systems, so which is called divergence. So at which point do we get completely different trajectories? And this is a measure of the sensitivity, sensitive dependence on initial conditions. So we'll talk about that some more when we're doing the assignments as well. Just a little bit about this deterministic part. So you would think that something that is deterministic is, of course, mathematically exact. That's still true. But what we have here is a limit on prediction, right? So we can, of course, always sort of do the post hoc prediction, right? So if I would have like, we have some papers here. So if you would, right, so if you would drop this paper and would have to predict mathematically based on the initial condition, which would be the height here, where it's going to end up, that would be very difficult. Because if I do it at the same time, look, this is the same initial condition, right? I hope. It's going to end up somewhere else. But afterwards, if we had a video recording of this, we would be able to calculate the trajectory, and it would be mathematically exact. So we understand why it took this particular trajectory, but what we would find is that there would actually be a very small difference in the initial conditions that caused this difference in the outcome. So much of the energy that goes into let's say real-world applications of systems that are actually chaotic, but also like the weather, is to get those measurements of the initial conditions as accurately as possible, because that's what will affect the predictability. So something that is chaotic in the deterministic sense is indeed showing disorderly behavior, and is extremely sensitive to small changes. So I already talked about this, but what you will see is that also in this logistic map you see this white band. It means that for some values you will see this deterministic chaos, then it will pop out again, and then after a while it will go back in. But why this is the case, that's the topic of research. I don't know a lot about that, but there are people who are studying why that happens at these specific values. So the thing to remember is you can have a deterministic system which can produce something that looks very random.
can I just, because I'm thinking in terms of behavior and behavioral interventions and so on, and
Yeah.
obviously several different initial conditions on different types of at baseline, for example, of an intervention, can predict how the people respond. But there are a multitude of different factors, the initial conditions of which might crucially influence the outcome. And so kind of identifying all the relevant ones seems like a...
Well, the clue is, and that's something we don't have really time to talk about, but I think the way a lot of people in ecology and biology, maybe also physics, think about this is that there might be systems that are inherently, or sub-processes that are inherently displaying this chaotic behavior. But then the thing is, okay, so what you're describing is that they are actually part of a coupled system, right? So what happens if you start to couple the dynamics? Then you are reducing the degrees of freedom of the individual processes, and then you can get stable behavior again. And so the idea, so the sort of overarching model here for understanding complexity in systems that are bistable is that you can have these chaotic dynamics going on, but there's like a coupling parameter that decides how they are interacting and how much they are interacting with one another. And this can still give you coherent and stable behavior. It can be pretty complex, but it will not be as chaotic as here. And the way this works is what you're doing by coupling the degrees of freedom of the individual processes, you get this pattern that is more well, it's actually less interesting. There's less possibility, less surprisal, but for being stable and coordinating your behavior, that's actually a good thing. But you also have to be able to let go again. So if you let go again of this control parameter, then you could get up in different states. And so let me go to the very famous model. So this is a continuous system, and it's made up of three differential equations. And this is the famous model that Edward Lorenz, there are several Lorenzes, but I think this is Edward, he's a computer scientist, and he was studying the behavior of the atmosphere, so this is telling you something about fluid dynamics, these equations. And as you can see, they're not very difficult. It's just in the continuous versions of these equations, you write a change over x is equal to a change over time. So that's the d just means difference. So you don't have discrete steps, but it's a difference. So and it's supposed to be continuous. But if you look at the other side of the equation, it just tells you that x, what's going on with x is some kind of function of what's going on in y and x itself. Right? What's going on in y is some kind of function of what's going on in x and what's going on in z and y. And then what's going on in z is some kind of function of what's going on in y and z. And what I mean by coupling is, so here are sort of the influence of both the history of x and what is going on in y is sort of moderated by this a parameter, right? So it's not fully the same, but it's sort of something is taken off, and the same here. So these equations sort of define how they are coupled. And the interesting thing is, so we had a very simple system, the logistic map, and for some parameter settings, you can see that it goes into this deterministic chaos. But that can happen only if you're working in discrete time. So the logistic map is just a one-dimensional system that can display deterministic chaos. In continuous time, continuous dynamics, you need at least 3 coupled equations to get deterministic chaos. And this is one of the earliest examples of it. So Lorenz was trying to model the weather, and then I think I've read about 3 versions of this story. So I don't know, I don't remember which one is the correct one, but I think there was like a fire in his lab, and he had to buy new computers, and he had all these results from this model. He had to print them out at the time, so he knew sort of what the outcomes were, and then he started to rerun the model. And he was studying the weather, right? So it's weather patterns, and he got completely different results. So he thought he was running the same models that he knew, but on these new computers, the results turned out to be completely different. But so first they thought there's something wrong with the computers. Those things were kind of expensive and maybe custom built even by IBM at those times. So they took apart the computers. That was not the problem. So in the end, he figured out that what the difference was that the reruns of the simulation had like 12 decimal point accuracy, and his original simulations had 13 decimal point accuracy. So that was the only difference. So just a rounding down at the 12th decimal point. And this led to the famous expression that this, if you want to compare what that difference is, this difference in initial conditions, that's like, a butterfly flapping its wings somewhere or not, can decide whether on the other side of the world you have a hurricane or not. Right? That's where this expression comes from, and it's based on this. So this is also called the butterfly attractor. It just happens to have these 2 attractor points where the system will orbit around. And this was one of the first displays of deterministic chaos, but actually it was already known that there are physical systems that have this. So this is a double pendulum. So it's just a stick that has 2 things where it can swing, and if you perturb it just a little bit, you get this nice. So this would be the state space. This is just looking at the angles here. It just has a nice pattern. It's nicely organized, nicely periodic. No problems there. But if you have like a medium displacement, it's still okay. Maybe there's some transient behavior there, but it'll settle in something that looks a little bit periodic. So you could probably also call this quasi-periodic, and not completely, but it's still it looks something like a limit cycle or a cycle on a torus or something like that. But now, if you have a large displacement, well, something else happens. So it becomes completely chaotic, and it becomes really unpredictable and extremely sensitive on the initial conditions. Right. So okay. So this is also an equation, right? So this is modeled in MATLAB. And a nice way to show this is if you have several of these pendulums, and you give them almost the same initial condition, right? So these are 3 equations, and they just changed very little bit the initial part, and you can see that there's at some point they start to diverge. And would I go there? Yeah, maybe now. Yeah. So here's the demonstration. Yeah, they already are doing something different right now. But that's what sensitive dependence on initial conditions means. So he holds them almost at the same point, but still there is some very small difference. It could also be a difference in air resistance, or maybe a little bit of the material. But it turns out that, so yeah, it's almost the same. But now they're already in a different state, right? So they're already not doing the same thing anymore. And there is a little catch here because these are also coupled here through this thing, but yeah, so it's not something that is just an oddity of mathematical equations. This stuff happens all the time, right? So there are many examples of systems that are, well, at least extremely sensitive to initial conditions. Okay, so yeah.
Question.
Yeah.
Yesterday you showed the example of the pebbles. What's the contradiction or difference between these two setups?
Of the what? Of the
The pebbles that free arrange themselves. In
oh yeah,
certain
the ball bearings.
Yeah, the ball bearings. Sorry.
Well, that's not. Yeah, so that is not a chaotic system, I think. No. But what you can say is that I think the organization they end up in is unpredictable. So that's emergent, and that is probably dependent on the exact configuration you start out with. So yeah, so there is some variation there that you probably cannot really repeat every time, and that will sort of decide with what it will end up in eventually. So there is a dependence there, but it's not extreme as here. Yeah.
Sure.
Yeah. So yeah, we've been looking at the assignments, right? And maybe you played around a little bit with these two models. So basically what you've been doing is generating time series, right, based on these models. And well, we would call this an iterative process. The way that this is implemented in these spreadsheets. So if you would do this, I don't know if people try to do this in R, but if you would try to do this, you would probably use a for loop or something like that, right? So you have some iteration and you can update the values. And so autocatalytic here means that we are assuming that the thing that is doing the iteration is just a flow of time. Yeah, so that's sort of, yeah, if there's an assumption, that's an assumption. But it's not very controversial assumption. Right, so this time series then is a record of these values generated by an iterative or a change process. Of course, by the way, this could be a random process, right? So the process could be draw a random number at each time step, right? Then you would have a random process. But, well, generally that's not what we encounter in nature. Oh yeah, so we talked about a solution. So if you have a model which has a solution, it can be very handy because you don't have to do the iteration. You can just fill in the numbers and you can immediately know the value you have at any time point. But very often we don't have solutions. If you remember this graph where there was this hierarchy of different dynamical systems, so the solvable differential equations is like, I think, category 2 or 1 maybe even. So it's not a large group of models, of systems you can model. Okay, and then at the very end, I don't know if everybody had a chance to get there. You were looking at a return plot of the data. I will show you an example in a moment. But basically what you're doing there is shifting the time series one time step and then plotting this as if it were a scatter plot, right? That's one way to study whether there's a structure in the dynamics that you're looking at. So one way to think of this return plot, but it's not really accurate. It's a very crude representation of the state space of the system, but just it's looking at the current state relative to the previous state. An actual state space or a phase space would be a representation of all the dimensions of the system, and then each coordinate in the space would be a state the system can occupy. So there is a difference between state space and phase space, but we're not going to talk about that. We're going to use that interchangeably. Now, if you found out that that the system is sort of well attracted to different regions of the state space, it's not going to all the possible states it could be in. You have a state space that is filled with attractors, and that literally means that the system is attracted to that state once it's near, right? So it's near that attractor in that state. It will have a tendency to go in there. The Quadratic method we did not discuss and will not discuss, so I can skip that. Okay, so we add this logistic map, and I asked you to look at the return plot. I don't know if everybody, was there anybody who got there? Yeah. What happened? What did you see? What did you see when you made the return plot?
For linear or logistic?
For the logistic?
Like this.
Yeah.
Parabola.
A parabola.
Points.
Did you expect to see that?
Not really.
Because it's like, yeah, you take this time series and then just, shift it one time step and then make a scatter plot and then you see this. You don't see a cloud of points. So why is that? Does anybody have an idea?
The transition equation is stationary, but it doesn't change. The mapping from the
the mapping.
value to the,
Yeah, so
if you call it transition equation.
yeah, so let me translate what I think you're trying to say. So what does not change is this rule, right? So this rule is the same always. So this rule is telling you what should happen from one time point to the next. The only thing that is changing is this little parameter here, so this gives you this qualitative behavior in time. But overall, the mathematical operations here are the same, right? So there is only one thing that can be in between each data point, and that's this formula, right? And what is this formula? So I'm talking about f here. So what is in between these data points? It's always this thing. It's always this thing. And what is this thing? Well, if you work out the parentheses, yeah, you'll see that this is L squared, actually. So this thing is not only called the logistic map, but it's also called the quadratic map. But I of course, did not use that term. And so this means that there's a quadratic equation that decides what the next value should be. And this means that these values can only be on a quadratic structure, which is the parabola. And that's basically the reason. So even though in time, when you look at this time series, it's completely chaotic, right? If you investigate, but what is the rule that is giving us this this behavior? It's a quadratic rule. So one thing to be wary about is, let me just put this up here. Yeah, so this is actually what you're doing, right? If you work out the parentheses. So it's just a quadratic function. Right, and it doesn't matter which parameter you have, it's always this quadratic function that is in between there. Oh, wait a minute, I have to go back, because I want to point out one thing that people usually, it's not the case if you look at these points. So here you have the time order, right? First you have this point, this point, this point. It's not the case that that's this point, this point, this point. These points might be here and there and there and there and there and there. This does not represent the time order of this thing here. So if you would sort of, if you would create like an animation or something in which these points would pop up here, you would see that this has nothing to do with the time order. Yeah, okay, so now I remember why that comment was on there about the cobweb method. You might want to look it up if you find a Wikipedia page about it. If you use the cobweb method to figure out this structure, you'll find that you'll see, so it's kind of a visualization that there's no time order in here. So this is time ordered, but where they end up is not time ordered. It's just the only thing they can end up is on this parabola, because that's this equation. So now it's kind of important that this is 1, right? So because this is 1, it means that this here is the maximum value. So this is a stylized function because we can make this 1. But this can actually also be a parameter, it can have any value. Yeah. So now we can go to the to the return plot quiz. Right. So what determines what is in between these points is a quadratic function. So what would happen if you make a return plot of the linear map? Think again. What is in between these time points? It's this function. You don't have to work out any parameters. It's just that function. So what would the return plot look like? Any ideas? Maybe someone actually checked it? A line.
Yep.
A line. So, yeah, the function that is in between these points, the change rule, the dynamical rule, the evolution parameter, whatever you want to call it, it's always just a linear function with a particular slope. And maybe a representation of the slope. It's not exactly the same thing. You could also think of y0, so the place where you start at maybe as a kind of intercept. Of course, they have a little bit of a different role, but if you would write it down with also y0, with the starting point in there, you would get something that looks like the equation for a line. Yeah, okay, so in because it's a linear change rule, you have a return plot that is a line. If it's a quadratic rule, you have a parabola. So now what happens if you have a cube in there? What would the return plot look like?
It's like dome shape.
It would be like this. This is a cubic polynomial. So yeah, and then you can go on and right. So that is actually well, it's one way to study whether there is any structure in your time series. Of course, in reality, you will not find this neat parabola. That would be very odd if you would have actually measured something and then it would turn out to be exactly this shape. But it is looking at the return plots is a very good first step into figuring out what kind of dynamics might be going on. Now, of course, oh, you don't have to remember this shape, but
So what if your data is so noisy that you just see a shotgun blast when you plot the return plot?
Then you have noisy data. Here we go. So, for instance, like this. So, what would happen if you would have white noise? So here the change rule is at the next step, at the next point in time, I just draw a random number from the normal distribution, something like that. Well, yeah, you can, if you make a plot, then you would expect this, right? So just your hail shotgun blast. And if you would make this longer and longer, you would see this would start to fill up and become nice round representation of the normal distribution or the bounds. But we can now ask, so this is at lag 1, but what happens if I take, not lag 1, but I shift it like 2, or 3, or 4, or more? So basically what I want to investigate there is, maybe there are different structures or different correlational structures going on if I look at larger lags in time. So, but this is white noise, so what do you expect for white noise? If you would take lag 2 or lag 10?
It doesn't change.
Yeah. I would also expect nothing to change. Right? It doesn't matter at what scale we're observing this random process, it will also always be a random process. Okay? Lag 500, yeah, you get less data points maybe, but it should always be this random structure. Okay. Oh, something was disappearing there. Okay. So now we take so this is lots of iterations of the logistic map. Right, this is the lag 1 return plot. What happens at lag 2 and lag 4? What do you expect?
It will start to shift a bit in between itself.
It shifts in between itself. Maybe you mean this. That's awesome. Okay. Yeah. So actually, what this is actually the second derivative of this, and this the third and fourth and fifth and so on and so on. Right. So of course, you will never encounter this in reality if you've measured something in reality. But to get back to your question, if there really is some kind of deterministic process, but it's covered with random noise, I would expect that actually if you would do a number of these things, that there would be behavior that would be different from real white noise. So you should be able to see that something else is going on than in white noise, and if it's not, then it's just white noise. Then it's equivalent to white noise. And another technique that is often used is what happens if you shuffle the data. So if your thing would look very random, but if you shuffle it, it becomes even more random, then there is still some structure there that you destroyed by shuffling the data. Right? So, but it's just covered under a lot of noise. Okay. Yeah. I think there's something wrong with the animation.